Okay, so we have located, we have calculated our first moment of area of 1, section 2, section 3. So I'm going to label this point at point A, and then we are going to find at our centroid. Okay, so we are going to determine where has the maximum Q over T ratio. Okay, where the maximum Q over T ratio is where the maximum stress will occur. Okay, so let's consider at point A, right? So Q over T. So at point A, the Q, you will have to do 27.5 times 10 to the power minus 6 plus 21 times 10 to the power minus 6. And the thickness now is twice of 10 millimeters. Okay, why twice of 10 millimeters? Is because of the left and right web. Okay, so 27.5 power minus 6 plus 21 power minus 6 is equal to 48.5 times 10 to the power minus 6 divided by 0.02. Okay, so it's got 2.425 times 10 to the power minus 3, and if we base on units, this is equal to meter squared. Okay, should not put a number because it's a ratio. Okay. Then at centroid, okay, so the first one is based on T mean. Okay, at the centroid is T max just divided by thickness. Okay, so this is equal to 27.5 times 10 to the power minus 6 plus by 21 times 10 to the power minus 6 plus by 10 times 10 to the power minus 6 divide. Now the thickness changes is equal to 0.05. Okay, so this will be equal to 27.5 power minus 6 plus by 21 power minus 6 plus by 10 power minus 6 is equal to 58.5 times 10 to the power minus 6 divide by 0.05. Okay, so 58.5 power minus 6 divided by 0.05. Now it's 1.17 minus 3. Let me do it again. 1.17 times 10 to the power minus 3. So from here, we know, okay, so we know that this value over here has the highest ratio at point A. So we can write this out. Tau max will occur at point A. Okay. So now we can determine V. So we know that tau shear XY at point A is equal to tau max. And this is equal to, given that is equal to 60 times 10 to the power 6, which is equal to Vy, which what we're trying to determine, over IZZ is 4.86. times 10 to the power minus 6, and then we use the ratio of 2.425 times 10 to the power minus 3. So from here, By will be equal to 60 times 10 to the power 6 multiplied by 4.86 times by 10 to the power minus 6. I want to be sure it's equal to 4.86. Yep. Divide by 2.425 times 10 to the power minus 3. Okay. So this will be equal to 60 power 6 times by 4.86 power minus 6 divided by 2.425 power minus 3 is equal to 120. Is it 120.247. Okay, so this is the value. So we are going to check. Okay, so you have to show a check. So check that at the centroid, right, the shear stress XY at the centroid must be less than 60 times 10 to the power 6 Pascal. Okay, you have to check. So a shear XY at the centroid will be equal to 120.247 times 10 to the power 3 divide by 2.425, divide by 4.86 times 10 to the power minus 6, then multiply by the ratio of 1.17 times 10 to the power minus 3. Okay, so 120.247 power 3 times 1.17 divided by 4.86 power minus 6 is equal to 120.247 power 3 times by 1.17 power minus 3 divided by 4.86 power minus 6 is equal to 28.948 times 10 to the power 6 Pascal. And this is less than 60 times 10 to the power 6 Pascal. Okay, let me do it again. 1.247 power 3 times 1.17 power minus 3 divided by 4.86 power minus 6. Yep. Okay, so the structure is okay. So this is a very, I think it's a very interesting problem to highlight that not necessarily the centroid will have the maximum shearing stress. Okay, and I think more important is this condition that we have to specify. Okay, where condition number 1, tau max can occur where the first moment of area is the maximum, or tau max can also occur when there's T min. So the most important thing, okay, and you should do this for your summary sheet, is your what? Is your Q over T ratio. This is so critical, okay, to I for the Q over T ratio. So any questions regarding this? So before I do stop, I want to sketch. I want to show you all the sketch of the shear stress, because it's interesting, isn't it, how this thing is going to unfold, or how the shear stress is going to look like. So if I'm going to sketch, I'm going to take this cross section. And we're going to view with a, I'm going to sketch. So let me draw our centroid, or sketch our centroid. Okay, so this is where our centroid is. Then I'm going to so this will be shear stress, and then we have our, again, this is just a sketch, okay? I don't have the equation, so I cannot specify numbers, only some points we are okay. So this is Y. So we have two position of concern. Not two, we have quite a few position of concern. So this is the top. Then we have and then we have so 2 points that we can be very sure. Okay, so I'm going to, so this is 0, 10, 20, 30, 40, 50, 60, right? We know that we have a point over here, okay? A point over here, it will read 60. And the other one will read 28.948. The other one will read 28. Okay, 28.948, 28. We'll read. Okay, so how this will look like is, okay, so the only these 2 points I'm sure, okay? So what will happen is we're going to see this, okay? And then we're going to stop here. And then it's going to be a stepwise function. It's going to be straight. Okay, again, this is a sketch, okay? So it's going to be a straight line up to somewhere around here. And then you will do this, okay? And then it will fall down here. It will go down again. Okay, it's going to be a straight line. And then it's going to do this. Okay. So if we were to take the whole thing, okay, and I'm going to copy, and I'm going to paste, and I have not tried this before. I'm now going to I'm going to rotate, flip vertical. Okay. So this is how the shear stress distribution will look like. It look like a rabbit. Okay, this is how the shear stress distribution will look like, just a sketch. Okay, so you can see over here for this case, because the fact that the thickness changes at this section over here, the thickness is different from the thickness over here. Okay, the thickness changes and then it go back to its original shape over here. That's why we have a shear stress distribution like this. Okay. So more important is, I would like to highlight over here, is the Q over T ratio. You have to be really careful with that. Okay. Right. So let's look at another example. Okay. So this is probably example 1, 2. So this is example 2. I think this is example 2. Am I right? I can't remember now. Let me look. Oh, example 2. So let's look at, before I go on to example number 3, anyone, any questions so far?
I have a question.
Yes.
How do you know the shape of the diagram? I mean, how do you know which one is curved, which one is a straight line?
So where the thickness changes, right, is a straight line over here.